Okay, hello everyone in a new video. So we have reached part 3 of chapter 3, which is the chapter of electric current for grade 11 students. And eventually we have reached section number 8. And the title of this section, which is the last section in this chapter, which is given by the quantity of charge, and the electric current I. So for this reason, in order to explain this section, so let me consider a section of a connecting wire. So we know that the wire is represented by simply a line, but now if we get closer to this line more and more, so this is a connecting wire. That's being traversed by a current I like this from left to right. So knowing that the connecting wire is a conductor, so what is a conductor? A conductor is a solid or a state of matter in which charges can move easily. Now if you consider a larger view of this wire, so on a very large scale, so this is the wire like this. And we know that the electric wire can be described, electric current can be described as a flow of water inside this current. So this is the electric current inside the wire moving like this from left to right. So this is the direction of the current I. So here for sure we have, okay, why do we have current? Because for sure it's connected across a closed circuit which causes the flow of electric current from left to right. But actually here what's happening inside of the current inside of the wire in order for the current to flow from left to right? We know that any matter is made up of small particles that are called, okay, it's made up of atoms. Atoms are made up of electrons, neutrons and protons, but now we are interested only in the electrons. So it's made up of small particles called the electrons. So inside this wire, electrons exist everywhere. So now if you need to consider the charge of this wire, so, or before defining the charge. Now till this moment we didn't give any definition for the electric current. We gave relation between different electric currents using the law of addition of currents or law of uniqueness of currents. Now we can explicitly define the current, and the current can be defined as I. So let me say the electric current can be defined in terms of the quantity of charge quantity of electric charge, let me say, because this is electric current, as the electric current, so this is the definition, is the rate of flow of charges with respect to time. So I is the rate of flow of charges with respect to time. So here what I'm saying that is that because the electrons are moving, yet till this moment I didn't specify whether the electrons are moving to the right or to the left. Now I'm just saying that because the electrons are moving inside this wire, this will causes an electric current I. So how can we define an electric current? So simply the electric current is given by I is equal to Q divided by T. Now what does each quantity represent? Let me say that where I is the electric current and its unit is given by A, which stands for amperes. Q is the quantity of charge. And we know that the SI unit of charge is coulombs. So probably, okay, nothing. Now as for time, T is the time or the duration, and its SI unit is S for seconds. Okay. So here I'm not sure how do we spell the name coulombs. Probably it's coulombs. I'm not sure of the spelling, okay? So let me write it this way, because I'm not sure of the spelling. So now what's the relation between Q and these electrons? So we know that whenever we have electrons, we can define a new quantity, which is Q, which is the quantity of charge, which is simply Q is given by N multiplied by E. So Q is the quantity of charge we know that any quantity of charge can be expressed as an integer number of the elementary charge. E is the elementary charge, and the value of E in the SI is fixed, and it's given by 1.6 times 10 to the power minus 19 coulombs. So what does E represent? It is the elementary charge, it's the smallest amount of charge found in nature. And what does N represent? N is the number of charged particles Okay, N is the number of charged particles having the elementary charge E. So we know that Q is expressed in coulombs and E is expressed in coulombs. N is unitless, it have no unit. Okay, probably you have seen also Q in chemistry. So what's happening here inside the wire? So we are interested only in two formulas that are given by I is equal to Q divided by T. This is the first formula. And the second one is that Q can be calculated. So here, for example, we are interested in determining the value of I. So in order to determine the value of I, we need to determine the value of Q and T. T can be measured using a stopwatch, for example, or it's given inside the exercise, and Q can be determined by the following formula, N multiplied by E. Okay? Now here, so from this formula, so what causes the current is the flow of charge in a given amount of time. So here the charged particles inside this conductor, which is the wire, are the electrons. The electrons are supposed to move from right to left like this, and always the direction of the electric current is opposite to the direction of the flow of electrons. So although the electrons are moving from right to left like this, but the real direction of the electric current is taken to be from left to right. Okay, so here what we should know is that I is equal to Q divided by T, Q is equal to N multiplied by E, and so these are the two formulas that we should know, and we should know the SI unit of each quantity. Moreover, we should know that if the direction of the electric current is from left to right, and the electric current, if the electric current is due to the motion of electrons, then the motion of electrons from right to left. So let me write here the following note. In an electric circuit, the motion of the electrons is the reason behind the electric current. The direction of motion of the electrons across the connecting wires or we can say in the circuit is opposite to the direction of a flow of the current. So that always the direction of flow of electrons is opposite to that of the current. Okay, so this is the last section in this chapter. Now we are ready to complete solving exercises. So we have exercise number 4. They are telling me in exercise number 4, in the adjacent circuit diagram the following voltages are given. We have that UBC is equal to 20 volts, UDE is equal to 4 volts, and UCA is equal to 8 volts. Now UBC is equal to 20 volts, then the trick in solving such type of exercises is to write applied voltage on the electric circuit itself. Now notice that here UBC, okay, is equal to 20 volts, so it's the voltage from this point to this point. So let me say that UBC is equal to 20 volts. Now UDE is equal to 4 volts. And UCA is equal to 8 volts. Okay, so now in number 1 they are telling me to calculate the voltage UAB. So notice that here UAB represent a DC voltage source, but they didn't, in doing so, they didn't want to justify which of these two represents the positive or the negative pole. So it may be like this or even like this. Now after we have, now we will calculate UAB. If UAB positive, then A is the positive pole and B is the negative pole. Now UAB can be calculated using the law of addition of voltages going from A to the point B. So let's apply law of addition of voltages. Then how do I apply this law? Always on the left we write the voltage of the battery, which is given by UAB. So the voltage that we are interested in calculating, and on the other hand side of this equation we write the voltages across different electric components going from A to B. So from A we'll go to the point C, and from C we will go back to the point B, because we know the voltage is UAC and UCB. Now if UCA is given by 8 volts, then UAC is given by -8. Here no need to justify that we have an ammeter of negligible resistance, because they directly give me the value of UAC, plus UCB Now here UBC is given by 20 volts, so UCB is given by minus 20 volts, so this is given by minus 28 volts. So the value of UAB is equal to minus 28 volts. So now notice that UAB is equal to minus 28 volts, which means that UBA is equal to 28 volts, which means that B is the positive pole and A is the negative pole. So let me write like this, and we have that UBA is equal to 28 volts. And now this is reasonable. Why? Because if you go from B to C we have 20, and from C to A we have 8. So this is 28. So we are done with UAB. Now we need to calculate the voltage UCD, so apply law of addition of voltages. So always on the left we write the voltage that you are interested in calculating, which is UCD. Then we need to go from point C to D across different electric components such that we know their voltages. Now we can go from C to A to B, and B directly to D, because across B and D we have a connecting wire. Okay, so as if the point B was present here, from B to D it is a connecting wire. So let me say from C to A, from A to B, and B to D. Now from C to A it's given by 8, from A to B it's given by minus 28, and from B to D it's given by 0. And here let me say that between brackets UBD is equal to 0, connecting wire. So this is equal to 8 minus 28, which is equal to minus 20 volts. So UCD is equal to minus 20 volts. So I repeat that the trick in solving such type of exercises is to write the applied voltage on the circuit itself. So this is minus 20 volts with the name of the voltage. Okay, don't forget with the name of the voltage. Now we need to calculate UCE. So let's apply the law of addition of voltages. So we are interested in determining the voltage UCE. Then we place it on the left. Then we'll go from C to E across different electric components such that we know their voltages. We can go from C to D and D to E. Notice that here in this case no need to mention that the ammeter is of negligible resistance, because they directly give me the voltage of UCD. Then from C to D and D back to E, notice that we have started with C on both sides, ended with E both sides, and we have placed D one time. So the value of UCD is given by minus 20, and the value of UD is given by 4. So this is given by minus 16 volts. So UCE is equal to minus 16 volts. And the trick in solving such type of exercises is to label the voltage on the electric circuit itself with the name of the voltage. So here UCE is equal to minus 16 volts. And finally we need to determine UEF. So let me apply the law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is UEF. And on the other side of this equation we go from E to F across different electric components such that we know their voltages. We can go from E to C directly because we know UCE, and from C to F, here in this case we need to explain and say that UCF is 0 since the ammeter is of negligible resistance. Although they didn't mention that the ammeter, okay, they didn't mention at the beginning that A is an ammeter, but we know that an electric component having a circle and carrying the symbol A is an ammeter. What is meant by A4? Just to distinguish between the different ammeters that we have, okay? That they didn't mention that the ammeter is of negligible resistance. It's okay, because we know that the ammeters are engineered in a way such that they have negligible resistance, because we have justified this previously in part 2 of chapter 3, and that the voltmeters are engineered in a way that they have very high resistance in order for each to measure the current and the voltage respectively. Now, going from E to C and C to F, so this is equal to UEC. If UCE is minus 16, then UEC is equal to 16, and this is 0. So UCF is equal to 0, the ammeter of negligible resistance. Here we need to specify the reasons, because we didn't discuss this previously. So this is equal to 16 volts. So UEF is equal to 16 volts. And let me write here that UEF is equal to 16 volts. Now in number 2, we need to specify the direction of the current in each branch and indicate the convenient polarities of each ammeter. So now, okay. So first of all, the direction of the electric current traverses the circuit from the positive pole to the negative pole. But the direction of the electric current can be determined by knowing the voltage across a branch. So now, let's start by the branch BC and specify. It means that we need to state with the justification. So let me start with the branch BC. So notice that in the branch BC, which is this branch, so notice that UBC is equal to 20 volts, which means it's positive, which means that VB minus VC is positive, which means VB is greater than VC. And let me here write from the beginning. Okay, let me erase this and let me write the direction of the electric current is from higher potential, in order just not to repeat for each of these branches, it will be a hectic task, from higher potential to lower potential. And now let me start with the branch BC. So notice that UBC is equal to 20 volts, which means it's positive. So VB minus VC is equal to a positive number, which means that VB is greater than VC. Then from B to C, the direction of the current. Now from B to D, okay, how should we know that from B to D? Because this is a connecting wire. Notice that from the battery it's being traversed like this, so it's for sure like this, okay? Why? Because now if you calculate UBD, it will be 0, then VB is equal to VD, but it's initially the electric current is coming from the positive pole, so it will be traversed like this. Now as for the branch DE, so we have that UDE is equal to 4 volts, which is positive, which means that VD minus VE is positive, which means that VD is greater than VE. Then from D to E, like this. So here also it will be like this, but let's verify it. From E to F, sorry, branch EF, So we have that UEF is equal to 16 volts, which is positive, which means that VE minus VF is positive, which means that VE is greater than VF. Then from E to F. So from F to C, so the ammeter is of negligible resistance. So if we need to discuss UFC, it's 0. So taking UFC alone to be 0, we cannot determine whether from F to C or C to F. So now noticing that in the branch EFC, so these two components are in series, so they are carried by the same current of same direction, which is from E to C. Now as for the branch DC, we didn't discuss DC. So the voltage UDC, if UCD is minus 20 volts, okay, we can take UCD is equal to minus 20 volts, which is negative. Then VC minus VT is negative. Then VC is less than VD, which means that the current reverses from D to C. Then from D to C, like this. Okay. Now from C to A, so from C to A, we have that UCA is equal to 8 volts, which is positive, which means that VC minus VA is positive, which means that VC is greater than VA, which means from C to A. Okay. So recall that we need to specify it means with justification. Now here notice that there is another part, the convenient polarities of each ammeter. We know that the ammeter, okay, so they are discussing the COM terminal. Always the COM terminal must be connected to the negative pole in order to give positive reading. So in this case, if this is the negative pole, so this is the COM terminal. Let me write them in blue. So going to the ammeter A2, this is the COM terminal. Going to the ammeter A3, this is the COM terminal. Going to the ammeter A4 to this terminal, okay? And here we can say the following statement, for example, as a justification, but here no need to justify. If the COM terminal is connected to the negative pole, then the ammeter indicates positive reading. Although they didn't mention whether the reading is positive or negative, when they don't mention, we take it always to be positive reading. Now as for number 3, they are telling me that the reading of A1 is 1 amperes. So let me remove the voltages, or let me keep them, and let me do the currents in blue or in red, it's okay. So the ammeter, the reading of A1 is 2 amperes, so it's positive because the COM terminal is connected to the negative pole. And notice that the ammeter is reading the current A1 traversing the branch CA. So I1 is equal to 2 amperes. They are telling me calculate the number of electrons passing through A1 in 1.5 seconds and the number of electrons corresponding for N. So in order to calculate N, So we know that Q is equal to N multiplied by E. In order to determine N, first we need to determine Q and E. Okay? Now E, we know it is given by 1.6 times 10 to the power minus 19 coulombs. So in order to determine Q, in order to determine N, first we need to determine Q. So notice that here they gave me the current, so I1 is equal to 2 amperes, and we have that T is equal to 1.5 seconds. This is the time T. So knowing I and knowing T, the quantity of charge Q can be determined from the following formula, knowing that we are interested in determining Q. Why we are interested in determining Q? Because we will use the value of Q to determine the number of electrons. So Q in this case is given by I1 multiplied by the value of T, which is given by 2 multiplied by 1.5. So this is given by 3. So because I and T are expressed in the SI, what's the value of Q and the SI is coulombs. So now that we have the quantity of charge traversing the branch CA is given by 3 coulombs. Okay, so if the quantity of charge traversing the branch CA is given by 3 coulombs, what about the number of electrons that are traversing the branch CA? And this can be done using the following formula: Q is equal to N multiplied by E, and we are interested in determining the value of N. So N is simply given by Q divided by E, which is equal to 3 divided by, we know that the value of E is given by 1.6 times 10 to the power minus 19. Plugging this fraction on the calculator, then we have that the value of N is given by 1.875 times 10 to the power 19 electrons. Then we have that N is equal to 1.875 times 10 to the power 19 electrons traversing or passing through A1, which is across the branch CA. Okay, so now in part B they are telling me the readings of A2 and A3 are the same. So what does this mean? The ammeter A2 is reading a current I2 of the same value, which is 2 amperes, and A3 is the same, which is I3 is equal to 2 amperes, and A4 reads the current I4 is 0.5 amperes. So here the question is wrong. Just let me check the question. And A4 reads this. So let me say that A4 is reading I4, which is given by 0.5 amperes. Okay, so just let me modify the question and let it be like this. The reading of A2 is the same, and A4 reads 0.5 amperes, and we are only interested in the reading of A3. Okay, So now in this case the reading of A2 is the same, so the value of A2 of I2 traversing A2 is given by 2 amperes, but this also doesn't work. So let me say the reading of A2, let me modify something. Let me say that the reading of A2 is I2 is equal to, say for example, 0.5 amperes or 0.1 amperes, and the reading of A4 is 0.5 amperes. So now the value of I2 traversing A2 is given by 0.1 amperes, and A4 reads 0.5 amperes. Now we need to determine the reading of A3, and this for sure can be done using the law of addition of currents. So in part B, apply law of addition of currents at node C. We need to specify the node at which we are applying the current, this law. So notice that in this case the law is given by summation of In is equal to summation of I out. What are the currents that are entering the node? They are given by I2, I3, and I4. Which is equal to summation of I out. The currents that are leaving the node are only I1, and we are interested in determining the value of I3. And then what's the type of this equation? This is a linear equation in one unknown. The unknown is I3. So the value of I2, okay, I3, the value of I2 is given by 0.1, which is denoted here, plus the value of I4, which is given by 0.5, and the value of I1, which is given by 2. So I3 in this case is given by 2 minus 0.1 minus 0.5, so which is given by 1.4 amperes. So I3 is equal to 1.4 amperes. Now why I have noticed that there is something wrong in this exercise, because notice that if I3 is taken to be 2 amperes, then something here will be wrong with the value of, say, if I2 is taken to be 2 amperes, there is something wrong with the direction of these currents. But notice that the direction of these currents we have determined using the potential, which is correct. Now if we have chosen I2 to be 2 amperes, if this is 2 instead of 0.1, then I3 will be given by 2 minus 0.5, which is minus 0.5 amperes, which is negative. Okay, which means that I3 is traversing the branch from C to D and not from D to C. But we are sure that the direction of the current is from D to C, because this direction has been determined from the voltages. Okay, so now let's move to the next exercise, which is exercise number 5. Now they are telling me the electric circuit and the adjacent circuit diagram consists of 5 lamps, a closed switch K, a 24 DC voltage source. Okay, a 24 DC generator and the connecting wires. Then the trick in solving such type of exercises is to write the applied voltage on the electric circuit itself. So here we have that the DC generator is 24 volts, so it's measuring from the positive to negative, so UPN is equal to 24 volts. Now in part A, they are telling me measurement of the potential difference. Part 1, an analog voltmeter of non-centered needle and dial D is equal to 100 divisions is connected across the terminals A and B. So the voltmeter is measuring the voltage UAB. Show the connections of the voltmeter, and here let me repeat, they didn't mention anything about the negative or the positive pole. So this is the voltmeter like this. So if they didn't mention anything about the positive or the negative pole, so we take it by default to be connected to the negative pole. So this is the negative pole going back to the voltmeter, so this is the COM terminal. Now this is done. Okay, done. Now in part B, they are telling me verify that this is U not V. Okay, verify that UAB is equal to 6 volt, knowing that the needle deviates, D is equal to 60 divisions. And the cursor, the scale is adjusted to 10 volts, and this can be done using the formula U is equal to S multiplied by D divided by capital D. We are measuring the voltage UAB, so this is equal to 6. 10 multiplied by 60 divided by 100. Plugging this on the calculator, then this is given by 6 volts. So UAB is equal to 6 volts. And the trick is to write the voltage here. Now notice that this is a closed circuit, then directly we can determine the voltage UBC. So indeed, in number 2 they are asking me about the voltage UBC. And this can be done by using the law of addition of voltages. Apply law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is UBC. And on the other side of this equation, we'll go from B to C across different electric components. We can go from B to A to B, A to P, sorry, and P to N, and N back to C. Now UBA, if UAB is equal to 6, then UBA is minus 6. Now UAP is 0 because across AP we have a closed switch. Now UPN is given by 24 and UNC is 0 because it's a connecting wire. So this is 24 minus 6 is given by 18 volts. So UBC is given by 18 volts. So let me label here that the voltage UBC is given by 18 volts. Now as for the voltage UDF, okay, so this can be also done by using the law of addition of voltages. So always on the left we write the voltage that we are interested in calculating, which is UDF, and we'll go from D to F. So we can go from D to A to P, P to N, and N back to F. Now UDA is 0, the reason is given by a connecting wire. Now UAP is given by 0, justified previously. UPN 24 and UNF is 0, and the reason is given by a connecting wire. So this is equal to 24 volts. So UDF, so let me write here that UDF is equal to 24 volts. Now in number 3 they are telling me deduce UDE and UEF knowing that they are identical. So we have the voltage UDF which is given by 24 volts. Knowing that L3 and L4 are identical, then they share the same voltage. Notice that in parallel to these lamps we have another lamp L5. It may be identical or not, but we are considering DF. Either we consider these two or we consider this alone. We don't consider that we have 3 lamps between D and F. For sure we have 3 lamps, but 2 of them are in series and 1 is in parallel with these 2. So we only consider these 2 without considering the lamp L5. So now let me say, since L3 and L4 are identical, then they have the same voltage. So how this is translated to a mathematical formulation? So what's the voltage of L3 is UDE. I'm moving in the same direction of the current, which is equal to UEF, which is equal to the voltage from D to F divided by the number of components, which is 2. Notice that here if we need to include UDF in this equation, we cannot include the voltage UDF, because here I'm using this equation based that we eliminate a point and we put the final point, the first point with the final point. Okay, first point with the final point, so which is UDF. Okay, so referring to this equation and reading it properly, that E is being eliminated and we start with D and with F, we make sure that we have used this formula properly, which is equal to 24 divided by 2, which is equal to 12 volts. So UDE is equal to 12 volts and UEF is equal to 12 volts. So this is it for part 3. Now in part 4 they are telling me N is taken as a electric potential reference, so the electric potential at the point N defined here is given by 0. In part A they are telling me verify that the 2 terminals P and A have the same electric potential, which means that we need to say that VP is equal to VA. So what do we have across P and A? We have a closed switch, so let me say that UPA is 0. The reason is given by closed switch. Then VP minus VA is equal to 0, which means that VP is equal to VA. So notice that this doesn't mean that the value of VP is 0 or VA is 0, but the difference is 0, which means that they are equal. So in this case, since VP is equal to VA, so here they are telling me verify, not why. If why, we can say directly connecting or close the switch, but whenever they say verify, we need to calculate. So then the terminals P and A have the same electric potential. Now in part B they are telling me to calculate the potential Vn, Vp and Vb. Let's start with Vn. So Vn is equal to 0, and the reason is given by reference electric potential. Now let me start with the electric potential at P. So in order to determine the electric potential at the point P, we need to consider another point in which we know the electric potential at that point and we know the voltage between them, which is UPN is equal to 24 volts. Now VP will appear explicitly here because UPN is written as VP minus VN, which is equal to 24 volts. Knowing that we are interested in determining VP, So Vp minus 0 is equal to 24, then Vp is equal to 24 volts. This is a linear equation and everything is expressed in the SI, which is volts. So we are done with Vp and Vn. Now as for Vb, add B. So in order to determine the electric potential at the point B, we need to consider the voltage, we need to consider another point in which we know that potential and know the voltage that relate these 2 points. Notice that here we have determined Vp, but we have, so Vp is 24, but the voltage at the point A, the electric potential at the point P and A are the same, because there is a close, we have proved that Vp, so we have proved that Vp is equal to Va, which means that we know the electric potential at the point A. So now UAB is equal to 6 volts. So now VB appears explicitly here. So VA minus VB is equal to 6 volts, which means that we are interested in determining VB. But now notice that VA is equal to VP is equal to 24 volts, which means 24 minus VB is equal to 6 volts. Here we will not place a unit, but it's the same. And we are interested in determining the potential VB. Then simply 24 minus 6 is equal to VB, so VB is equal to 12 volts. Okay, I repeat, we have used the voltage UAB because we know the potential A, which is equal to the potential P, and P we determined previously, which is given by 24 volts. Now in part 5 they are telling me an oscilloscope is connected across the terminals of the generator. We observe a horizontal line which is displaced upward. This is important, by 2.4 volts. Show the connection of the oscilloscope. Now because it's displaced upward, then it's measuring positive voltage. Positive value, and knowing that the positive value is given by UPN, then the oscilloscope measures UPN. So calculate the adjusted vertical sensitivity knowing the number of divisions, and we know the voltage UPN. So simply we have that U is equal to SV multiplied by Y. We are interested in determining the value of SV. So SV is equal to U divided by Y. We are measuring the voltage UPN, which is equal to, so the value of UPN is given by 24 divided by 2.4. So this is given by 10, right? Because everything is given in the SI and Y is expressed in divisions, not centimeters, so this is volts per division. So SV is equal to 10 volts per division. Now as for part B of this exercise, they are telling me applying the law of currents, determine the intensities of the currents I2 and I3, knowing that I is 2 amperes, I1 is 1.25 amperes, and I5 is equal to 0.5 amperes. So here we need to determine two currents, I2 and I3, which means that we need to apply the law of addition of currents. How many times? 2 times. Now I2 can be simply determined by applying the law of addition of currents at the point A. So we have that summation of I in is equal to summation of I out. Notice that we are applying at the point A what are the currents that are entering the node I, and what are the currents that are exiting or leaving the node. They are given by I2 and I1. Knowing that we are interested in determining the value of I2, the value of I is given by 2. I2 is kept as a variable, and the value of I1 is given by 1.25. Then I2 is given by 2 minus 1.25, which is equal to 0.75 amperes, because everything is expressed in the SI. So the value of I2 is given by 0.75 amperes. And now we are interested in determining the value of I3, then applying the law of addition of currents at node D. Because the entering is I2, the leaving is I5, we know them, it's left to determine I3. Then apply law of addition of currents at node D. Then summation of I in is equal to summation of I out. The currents that are entering are given by I2, the node. Leaving are given by I5 and I3. And we are interested in determining I3, so it's kept as a variable. I2 is given by 0.75, the value of I3 is given by 0.5 plus I3. So I3, this is 5, is given by 0.75 minus 0.5, which is equal to 0.25 amperes. And by this we have finished solving this exercise. So that's it for me in this video, guys. See you soon in a new one.